Yeah, welcome.
Good evening, everybody, those from India, and good morning to Professor Jerry Lips in California, USA. Friends, we are inaugurating the Earth Science Week organized by Maharashtra Vriksha Samvardhini, an NGO from Pune. And this will be followed by a number of lectures in these 3 days. This year, we are having a theme that is science through philately. Usually, every year we follow this particular activity as a part of Earth Science Week. This Earth Science Week was founded by American Geoscience Institute AGI in 1998 to promote understanding and appreciation of Earth science. This was meant for allowing masses to know about the green Earth, to know about the environmental awareness and improvise that all over the globe. As I said, this is an activity followed all over the globe in different languages. The AGI also partners with number of educational institutes, which is Maharashtra Vriksha Samvardhini is one of them, in order to have number of activities, lectures, etc. for the masses. In India, especially in Pune, Maharashtra Vriksha Samvardhini, which was founded in 1989 by Dr. V.D. Vartak, an eminent botanist in India. And in order to increase the awareness of green earth amongst masses, amongst students, he had started this Maharashtra Vriksha Samvardhini. For last 8 years, MVS is organizing number of lectures during this Earth Science Week. This year, the theme for this particular activity is education through philately, that is on stamps. In Marathi, the only book probably written by Prof P.V. Vartak, Dr. P.V. Sowani, that is Vice Principal of Ferguson College, is based on the philately in Marathi language. This year happens to be the birth centenary of Prof P.V. Sowani from Ferguson College, and in his fond memory, this activity is dedicated to his loving memory. Professor P.V. Sowani was Vice Principal of Ferguson College right from 1954 onwards till 86. He did his BSc, MSc from Pune University. In 1958, he was awarded Fulbright Scholarship to USA in Colorado School of Mines, there where he studied the specialized geological information, and that after coming back, he carried out his activity of spreading the knowledge of geology all over, and he was the most popular teacher in geology in Ferguson College. He also was, if I'm, can you show the slides please for P.V. Sowani? Professor P.V. Sowani, I happened to be his student in 1976 to 1978, a very popular teacher in geology. And if you ask any of his students, probably they would say that he would make his geological teaching colorful by giving examples from movies. For example, I remember he used to tell us, yes, if you have seen Johnny Mera Naam, then Pran and Devanand, they are fighting with each other on laterites. Or if you have seen Sholay movie, then at the background, when the fight is going on between the Dharmendra and his enemy, Amjad Khan, then those are fighting on batholiths of granite and so on. So he would give such an example that would have an imprint on the student's mind lifelong. He made his debut in Ferguson College in 1954. Next slide, please. This is some of his pictures during his fieldwork, and very popular teacher to explain geology in the field as well as in the class. His information used to be home friendly because he would give examples of dove, or he would give examples of household events where geology can be best explained. Of course, in the field, whether it is columnar joints or anything else, he would give examples from movies. Next slide, please. As I said, in 1925, he was born, and therefore this is the birth centenary for Professor P.V. Sowani. He studied in SP College and then earned his BSc degree from chemistry and geology from Ferguson College. Completed his MSc in geology from University of Pune. Next, if you see in early stages, this is from 1962 to 64. He was a part of teaching in geology in Ferguson College. He was head after 62 and till his retirement, he became vice principal, secretary of Deccan Education Society, as well as he was in the as a head of postgraduate department of geology from till 62 to 65. Next, please. 59 onwards, he became a life member of Deccan Education Society, the parent body of Ferguson College. Served as a vice principal of Ferguson College for 12 to 13 years. Served as secretary of Deccan College for 3 years, and so on. Next, please. In 1940 onwards, he began his science writing. A very popular teacher in Marathi science information, what that he gave. He authored about 30 books, and more than that, various scientific articles he had written in number of magazines, newspapers, etc. He was advisory for Shrushti Jnan and of course Vigyan Yug magazine, and there he contributed a lot that speaks volumes about his spreading knowledge of geology amongst masses or students. Next, please. Active member of Marathi Vigyan Parishad, Pune division, and Marathi Vigyan Mahasangh, that he was a part of the governing body. Member of number of World Book Encyclopedia, that is Vishwakosh. He was there for 25 years and he has written a number of articles in Vishwakosh, which you can read anytime. Long-time member and one-term president of Jyotir Vidya Pratishthan. That means his knowledge and his information about the palmistry or astrology also gave him different writings in different languages, especially in Marathi. In English, he contributed a lot in the form of some research papers. Next. All his Marathi books were meant for studying geology at early stages. And therefore, if you are a school student or a college student, these would help you to understand the geology of Maharashtra, different aspects of geology, and of course, the information that he spread amongst masses. So that speaks about his knowledge and his prophecy over these subjects, and his contribution in Marathi is practically uncomparable. Next. Not only that, he made number of students to initiate writing in Marathi, especially Dr. Niranjan Ghate. Probably he would express his views in a few minutes. He also was one of his best students who had acquired information and tried to follow his instructions. These are some of the books that Professor Sowani wrote in Marathi for the sake of providing information in science amongst students. Next, please. This year, Science Through Philately is the theme that Maharashtra Vriksha Samvardhani has decided to have. And Professor Sowani was amongst the only, probably the writer in Marathi who has written something on philately. And that he has contributed in Marathi language, so that even Marathi students, they can learn about the philately. Professor Ajit Vartak is one of our best philately contributor in India. Next. This is where Professor Sowani's commemoration fund was raised by Department of Geology and handed over to the Deccan Education Society. This fund helps students to go for their fieldwork, or it also helps needy students whenever they are required to have money if they are not having. And that also takes care of the activities that every year the college is running regarding functioning of the Earth Science Week. Next. These are the different photographs of Sowani sir. And as I said, when he introduced Devanand to us, probably for us, he was a Devanand in geology. and always a very smart personality and very soft spoken, and his vocabulary was tremendous. Next, I now have one of his student, Dr. Niranjan Ghate, who has authored more than 130 books in science in Marathi, probably would like to express his views on his teacher, probably most popular teacher amongst the students of that time. I request his clip to be shown to the authors, to the audience.
मला वाटतं आपण आता ही क्लिप नको दाखवूया, ती नंतर आपण YouTube वरती अपलोड करूया, कारण ओरिजिनल साऊंड आहे तो खूप बारीक आहे.
ओके ओके,
त्यामुळे ते ऑडिबल होत नाही.
Okay, okay. Then I think we'll go ahead then.
Friends,
Yes.
because there are some technical problems regarding the audibility of this particular clip, we would show this on YouTube later on, and all the activities of Maharashtra Vriksha Samvardhani are already there on the YouTube.
Mission Devrai. Mission Devrai channel.
Mission Devrai, under Mission Devrai, they have been shown. So you can have this particular one after the event is over. Now I request his son, Mr. Aniruddha Sowani, to express his views on his father. Mr. Aniruddha, please.
Okay, I think then Uday, you go ahead then.
Okay.
Probably
when he joins, we will have his views audible. Now I request we would have our inaugural speech by Professor Jere Lips, and I would request Dr. Nicole from Goa to introduce. I would request Ajit Vartak to introduce Mr. Professor Dr. Jere Lips. Ajit Vartak, please.
Good evening, everyone. It is my great honor to introduce today's speaker, renowned earth scientist, Professor Jere Lips. Professor Jere Lips did his doctorate from University of California, Los Angeles. Then he was leader of 2 projects on Antarctic marine ecology for United States Antarctic Program between 1971 to 1981. As a result of his research in Antarctica, an island in Antarctica is named after him as Lips Island. His research mainly concerns with paleontology, geology, evolutionary biology, ecology of modern and marine organisms from places around the world. Presently, he is a professor emeritus of the Graduate School, University of California, Berkeley, and curator of paleontology at the University of California Museum of Paleontology. He has published more than 500 research papers and articles and authored many books. He has been visiting professor in Oxford University, University of Georgia, University of Tübingen, Germany, Aarhus University, Denmark, Paleontological Institute, Russia. He has been visiting scientists in Natural History Museum, Washington, D.C. and Natural History Museum, London. He served on NASA's Planetary Protection Committee. He is a fellow of many prestigious institutions. Some of them are Shell Foundation, Cushman Foundation, Geological Society of America, California Academy of Sciences, Friend of Darwin. One foraminifera genus, Lipsina, and one species, Concris lipsi, are named in his honor. He is a living inspiration to all of us as he continues to work on his research papers and articles at the age of 86. With this short introduction, now I request Professor Lips to give his talk. Professor Lips.
Thank you very much. I'm very privileged to be with you this morning here and evening there. And I'd like to summarize some of the features of geology that has gone on in the past. Let me set this. There we go. So I'd like to speak to you today to give you a summary of the past, the present, and the future of earth science and geology in particular. So one of the first things that happened to me in graduate school was a meeting between a British speaker and the geology department at UCLA. The British speaker was a prominent man who promoted not plate tectonics, but continental drift. After his talk, two of our professors stood up and each of them gave about a 40-minute response to that, saying that there was no such thing. Well, in about 1963 through 1968, the theory of plate tectonics was developed, and within 1 year, those two people accepted plate tectonics completely. One of them had written a paper called "Fossil Plants Indicate Stable, Not Drifting Continents." Another couple of years later, he wrote a paper, "Fossil Plants Indicate Drifting, Not Stable Continents." So plate tectonics has become the basis for almost everything we do in earth sciences. And you can see here that we can reconstruct Earth history and the position of the planets. This shows the progression of plate movement from the end of the Paleozoic to today. We can also do this all the way back to about 1 billion years, although there were not many plates at the time. But this has been a very useful thing for geologists, paleontologists, and biogeographers in the modern day. So here's the geological time scale. All of these names were proposed for rocks before we knew their actual age. Around the turn of the century, the 1900s, it became possible to radiometrically date rocks. And so what I've given you here is the dating on all of these rocks from the modern all the way back to the beginning of Earth at around 4,550 million years ago. We can see that there's been a big radiation of animals, and only 1/9 of the Earth's history is recorded in the Phanerozoic. That's the time from which larger animals have been on Earth. Prior to that, there were a few invertebrates at the end of the Proterozoic, but most of the things that we see back then were bacteria or single-celled eukaryotes. Paleontology was changed by plate tectonics, that's for sure, and we discovered fossils. For example, these are Ediacaran fossils from the White Sea in Russia, and you can see these are really the first animals, an assortment of the first animals. There are a lot of other ones that have been discovered in the intervening years. So we're transitioning here from a time of mostly description of geological features in the past to the present, and now moving on to the future, we'll see. One of the most important things that we've discovered so far in the present has been our changing climate. We know that this is a difficult topic in the United States and perhaps a few other places in the world, but we do know that the climate has been changing for a long time. Our geological record shows that it changes, but starting in the industrial era, humans have contributed a great deal of CO2 to the atmosphere. So we have both nature through the sun and the Milankovitch cycling, and us polluting the atmosphere with CO2. The CO2, of course, traps, as do the other greenhouse gases, the heat in the atmosphere, in the soils, and in the oceans. This shows the increasing amount of CO2 from 1860, as you can see, to greater than 2025. Now it's about 427 parts per million. It started back at about 280 parts per million, and that was what it was throughout the entire Pleistocene, about 280 to 300 parts per million. And that's what we all grew up with, something less than that, or more than that, excuse me. So that when most of us older folks were born, there was 300 to 310 parts per million. And now it has shot up since 1960, all the way to 427 parts per million. This climatic change is shown here in a inference of the heating of the entire globe in 2024. And you can see there's hardly any places that haven't heated up. The land surfaces, the oceans, all of these have heated up greatly. And we have no solution to this problem because CO2 is continuing to accumulate in the atmosphere. And it's especially getting bad because it's now beginning to cause other greenhouse gases to be released from things like permafrost. And that releases a lot of other gases as well that contribute to this. We got to end this because this is sufficient now to probably wipe out the cycling that we saw throughout the Pleistocene, and we don't have any way to stop this at the moment. Will it just end up roasting ourselves? Will this get up to 1,000 parts per million? And what will the temperatures look like? This is our future. We've got to worry about this. This is the most important thing that all of us as earth scientists can contribute to, and especially contribute to public understanding of this phenomenon. It's the end of us if we don't. Many of us won't be around to see how that goes, although it would certainly be interesting. But our families, our children, our grandchildren, our great-grandchildren, and all the rest of our descendants will be subject to this heating if we don't control it now. So the best thing to do is to continue our efforts to control it, but also try to figure out how to best adapt to not just warming climates, but all the things that it brings with it, like the rising seas as the oceans warm up and the glaciers in Antarctica and the Arctic and other places melt. Sea level will rise. It could rise if Antarctica and all the other ice melted by 280 feet. That's big. During the Pleistocene, 125,000 years ago, sea level rose just 8 meters around the world. And you can trace that in various parts of the world. So I think this is our future that we really have to deal with. But I'd also like to talk. I'd also like to talk about. I'd also like to talk about what's going on in astrobiology and astropaleontology. This,
Sorry,
I wonder if it, yeah, could
somebody
everybody mute,
is
please?
talking.
So another thing that's in our future in geology and paleontology deals in the future with astrogeology and astrobiology, and for us, astropaleontology. It'd be nice if you could mute yourselves, please. So this is the search for life in the universe. And I want to concentrate not on the geology. I want to concentrate on astrobiology and paleontology, just because I do that a lot myself, and we'll be speaking about it later this month. Searching for life in the universe. This is the universe in the background here. There's 125 billion galaxies with more than 100 billion stars in each one. If you multiply these numbers together, you can see that 125 times 10 to the 20th stars. That number actually has a name, sextillion. So there's 12.5 sextillion stars in the universe. Of those, each one has 1 to 5 or 6, 7 planets or more. And if we assume that all the planets had all the stars had 5 planets, that would be 62.5 sextillion planets or more. We know that there are almost 6,000 exoplanets so far, seen by the Kepler scope, and confirmed by tests, 677. 30 of these are Earth-sized planets in habitable zones where water comes in all 3 of its forms. And these are the ones that we're particularly interested in looking for life, extraterrestrial life. I think this is another really important one. And we have 2 spaceships going to, one is already on Mars, and another one is on its way to Europa. And the one on Mars has been collecting cores to bring back to Earth in 2030, 2035. That depends on funding for NASA and whether or not we have any scientists left at NASA. The European Space Agency is involved in these as well, so perhaps these will get carried out no matter what happens in the United States. So Mars is a logical target for many reasons. We've had many probes, many satellites going around it, and there's a lot of possibilities for life there. Not living life, unless it's buried in the subsurface, but fossil life. There are plenty of places with sediments that look good. On Europa, this is the 6th big moon of Jupiter that Galileo first discovered, the 4 of them. Europa is about the size of our moon. The surface of it is about 60 million years old, and it's got these big cracks you can see there, and a couple of craters here and there. And underneath the icy crust is an ocean that has more water than our own ocean, maybe 4 times as much. So that there's a possibility for life on Europa. And maybe this Europa probe that they were sending that'll arrive at Europa sometime in the early 2030s. These are really exciting times. Everybody has always been interested in extraterrestrial life and we may solve this problem in the next couple decades. Let me mention just in passing here about world population. This is the other big problem that's facing us. And as geologists, we will be trying to deal with this number of people all working on the surface of the earth in one way or another, so that it becomes a problem, as I said, for geologists. We see that just in our lifetime, since, let's say, 1960, there were 3 billion people on Earth. And in just that time to 2030 or 2025, there's now 8 billion people on Earth, 5 billion more. Actually, 6 billion more than when I was born. This can't keep up. This is a projection at the same rate we're growing today, that we'll have almost 10 billion people in the year 2050. We got to stop that, or learn how to deal with those kinds of numbers, 10 billion people that our children will see. So our children have to deal with the climate change, and they have to deal with populations. And in ending, let me talk about one of my favorite things, and that's been introduced to me by Ajit, and that's fossils and geology on stamps. And I show 2 slides of these slides showing stamps. These are fossil bivalves, various kinds of clams. And then we have a stamp that's devoted to human evolution. And there are thousands of stamps. When Ajit and I wrote a paper about this, along with a few other people, I think there were 4,000 stamps with fossils at that time. And that was about 5 or 6 years ago. I think that the rate of printing of new stamps has accelerated, and it's a fine hobby to have for people who are interested in geology or any other science. Stamps are a fabulous way, as we heard in the introduction to this session, to get people interested in geology, paleontology, biology, and so many other sciences. Well, thank you very much. I have enjoyed my time with you this morning, your evening. Thank you.
Thank you, Professor Dr. Lips. It was a very valuable information, and of course, precautionary measures have to be taken if we want to see the future of geology on this earth. Thank you very much, sir. Friends,
You're welcome.
This event has been organized by 4 departments, that is Department of Geology, University of Pune, Department of Geology, University of Goa, Ferguson College and Autonomous College, and of course the Maharashtra Vriksha Samvardhini. Now we will have our first lecture in this regard, and that is by Mr. Avati, Arvind Avati from Atomic Mineral Division. And I would request Dr. Nicole from Goa University to introduce the speaker. Dr. Nicole, please.
Thank you, sir. It is my privilege to introduce Mr. Arvind Avati, our speaker for today. He's a scientific officer retired from Department of Atomic Energy and a former consultant of the Ministry of External Affairs, Government of India. Mr. Arvind Avati obtained his MSc degree in geology with distinction from University of Pune in 1978, and he has worked as a scientific officer at the Atomic Minerals Directorate and the Strategic Planning Group of the Department of Atomic Energy, that is DAE, from 1979 to 2013. He has also worked as a consultant to the Ministry of External Affairs, Government of India. His specializations include uranium exploration, planning and management of planned projects of DAE, nuclear laws, non-proliferation, and export controls. He has 22 years of vast experience in uranium exploration and has made outstanding contributions in the field of exploration, such that he has discovered, or he is responsible for the discovery of 2 uranium deposits in Meghalaya and a number of occurrences in eastern and northeastern India. He has also guided uranium exploration program in the eastern and northeastern parts of India. He was the head of the Planning and Management Services Group of Atomic Minerals Directorate from 1998 to 2001. He has worked for 13 years in Strategic Planning Group during 2001 to 2013 and handled issues related to uranium exploration, augmentation of uranium resources, demand and supply of nuclear fuels for PHWRS, mining of uranium, beach sands and rare earths, nuclear fuel cycle related activities, and planned projects of industries and mineral sector of DAE. He also has handled issues relating to nuclear laws, non-proliferation, and export of controls, bilateral discussions with other countries, nuclear suppliers group, UN Security Council resolutions, particularly the UNSCR 1540, and the multilateral export control regimes. He has played a key role in formulations and drafting of the nuclear laws and regulations, such as Weapons of Mass Destruction and their Delivery Systems, Prohibition of Unlawful Activities Act 2005, Nuclear Control List, Revision to SCOMET list, that is the Special Chemicals, Organisms, Materials, Equipment and Technology, Guidelines for Nuclear Transfers, the Civil Liability for Nuclear Damage Act 2010, and such related rules. He was also a member of the Uranium Group of IAEA Vienna, Consultative Group NFCIS of IAEA, Export Control Working Group of ITER Council France, and Advisory Committee on WMD and their delivery systems. He has participated in a number of international meetings and discussions as member of in the Indian delegation. He has also published and presented several research papers in national and international journals, seminars on uranium, nuclear laws, and associated subjects. For his vast experience, he was also awarded the Special Contributions Award 2006 from the Department of Atomic Energy for contributions in the field of nuclear sciences and technology and to the program of DAE. So this award was presented to him by our then President of India, Dr. APJ Abdul Kalam. So I welcome Mr. Avati. Thank you for accepting our invitation to have this lecture, and we are very excited to hear about rare earths from you, sir. I leave the floor open to you, sir.
Thank you. Hello, everyone. Good morning, good afternoon, and good evening to all participants of this session, wherever you are located. I am Arvind Avati. Let me begin by thanking the organizing committee of this event, and especially Dr. Ajit Vartak and Dr. Uday Kulkarni for giving me an opportunity to talk on this platform. I feel privileged to be here for the Earth Science Week 2025, which is being celebrated on the occasion of the birth centenary year of Professor Sowani. He was my teacher who taught us mining geology. I am going to talk about a very interesting and important topic, which has attracted the attention of world leaders during the last 2 decades, that is the rare earths. Our daily lives depend on rare earth elements. These are little known metals hidden inside the technological applications we use every day. They are used in everything from smartphones, laptops, electric cars to wind turbines and fighter jets. During past 2 or 3 decades, they have quietly become one of the biggest strategic challenges in the modern world. The story of rare earths is not just about science, it is also about economics, security, sustainability, and global power. So, now let me start by telling you about how they reached this status. Now, I will start my presentation. Yes, I will begin with the is very interesting and important story on this rare earths resources, applications, and geopolitics. This so happened that in 2010, rare earths suddenly became notorious overnight. Till that time, many people outside the geological community or technological community or industries associated with rare earths were hardly knew about these rare earths or were unaware of these materials. Actually, what happened since 1990 onwards, China has almost a monopoly on these rare earths. Their production share in the world is around 97%, which exerted a great influence of global REE market. This type of domination is unparalleled in the history of strategic materials. The fact that one state or one country alone holds such a near monopoly is a unique case. Actually, in September 2010, what happened is a maritime incident took place between China and Japan. A Chinese fishing trawler entered into a disputed area of East China that is called as the Senkaku Islands area. And they rammed into Japanese Coast Guard vessels. Some skirmishes took place, and as a result of that, Japanese Coast Guards arrested Chinese trawler and crew members. On this issue, China reacted by arresting 4 persons from Japan and also halted exports of rare earths to Japan. This happened in September end, that is of 2010. And subsequently, China also restricted export of rare earth elements to European Union, United States of America, and also other countries in October 2010. They stopped exports or restricted exports to EU and USA mainly because Japan started resourcing REEs from EU and USA, which were actually supplied by China. So this was sort of a re-exporting diversion. So they stopped it. And this caused worldwide shortage and created anxiety among manufacturers of high-tech equipment because majority of the world, these high-tech equipments were all imported from China. And because of that, although China did not declare this as an embargo, this was an embargo situation. They informed the world that we are going to have export control quota, export taxes, and various other restrictions on mining of rare earths. But this created a global rare earth crisis. And this period was considered as from 2010 onwards as a global rare earth crisis. Now, what are these rare earths and how they are important for us? We'll see it. Looking at this one, actually these rare earths are a group of 17 chemically similar elements. In the periodic table, if you look at it, group 3 elements, they start with scandium, yttrium, and then lanthanum. And in the same lanthanum to lutetium, these elements are positioned, and next is actinium series elements. So out of these, in this third group, the 17 elements that includes 15 lanthanum to lutetium elements and scandium and yttrium also, because all these elements have similar chemical characteristics. As a result, scandium and yttrium are also included in lanthanoid group. And collectively, all these 17 elements are called rare earths. They are called by various other names. They are called rare earths, rare earth metals, or simply rare earth elements. But one and the same, whether you call rare earths, rare earth metals, or rare earth elements, they are one and the same. But this terminology or term used rare earths is a misnomer, mainly because neither they are rare nor they are earth materials. In the sense, when they were discovered, that time they were found in the Ytterby area in Sweden, and they were considered as very rarely available materials. So the terminology rare was used. At the same time, initially they were called as earth materials. Earth materials means in the periodic table, group 2 elements are called alkaline earths. So as per the initial experiments and all that, these rare earth elements were put along with those alkaline earths. So they were called earth materials. Subsequently, it was later on experimentation and all that, they were known to be not a part of group 2 elements, but they were part of transition elements. But within the transition elements as well, they are not actually within the transition element, they are inner transition elements. That is only the lanthanum series and actinium series elements. Those 15 elements in lanthanum and 15 elements in actinide, these 30 elements are the inner transition elements. So anyway, that was the chemical part. So these rare earths are divided into two main groups, that is LREE and HREE. LREE means light rare earth elements, HREE means heavy rare earth elements. This classification is very arbitrary based on their atomic weights. Lanthanum to uranium, when you look at the round, this thing, when I have shown in the lower part of this present slide, lanthanum to europium, they are put as the LREE, whereas gadolinium to lutetium, they are called as a heavy rare earth elements. In these heavy rare earth elements, yttrium, which is the another group in the group 3, that also has got similar properties like the heavy rare earth elements. So it is also included in heavy rare earth elements. With regard to abundance, actually, lighter rare earths with even atomic number are more abundant. They are more abundant. They are more abundant than those with the odd number rare earth elements. Besides that, these rare earths are also incompatible. Incompatible in the sense because of their ionic size, their large ionic size elements, so they do not crystallize in the magmatic they remain in the magmatic liquid phases or molten phases, and they crystallize in the later part of the magmatic phase or crystallizing phase. So lighter elements are more concentrated in the crust compared to the heavy rare earth elements. And because they have got chemical similarity with each other, they can substitute for one another. And due to this, they can occur within a single mineral. Till date, separate rare earth element as such has not been found anywhere. They always occur in a group, whether their abundance or occurrence is more or less, less or more, but they occur together. This is the rare earth elements. Now, they represent very remarkable property. These rare earths represent very, very remarkable property. They exhibit the unique set of properties such as chemical reactivity, catalytic efficiency, magnetic properties, optical brilliance, as well as corrosion resistance that allow them to play a very central role in industries across the world. They are silvery white, relatively soft metals, often tarnished in air. They have got high densities as well as high melting points. Many rare earths have strong magnetic moment, and as a result, they are the key components of the strongest permanent magnets in the world. They are electropositive elements. As such, they are very highly reactive, and because of this reactivity, they make useful as a catalysts. They are oxyphile or lithophile elements. They have got strong affinity for oxygen, and which helps them in making stable oxides for ceramics, glass, and polishing powder. They produce unique emission spectra, colors, when stimulated by electromagnetic radiation, and they produce brilliant colors. With regard to their applications, these rare earths were actually, before starting with the applications, I'll give some background. Majority of the rare earths, barring some 3 elements, all of these elements were discovered in the 19th century. And their first industrial application was in the 1897 in the form of incandescent mantle, gas mantle lamps. That in our India, we call it as a Petromax lamps. The Petromax mantle were manufactured using these rare earths. These mantles were manufactured using thorium oxide and cerium oxide obtained from monazite mineral, which is radioactive mineral. Subsequently, after that, to ignite these mantles, to provide them as an ignition method system, flint stones were developed. Flint stones are alloys of mish metal and iron, and they were used for ignition as an ignition system for these mantles. And later on, these flint stones were also very popularly used in cigarette lighters. Since 1891 till date, nearly 10 billion mantles have been produced in the world and have been consumed. Apart from that, these rare earths were used for enhancing intensity of light, especially for searchlights, which earlier days we used to see in the circus and all that. They used to have the searchlights or various other activities, motion picture projectors, and also in the carbon arc lamps. This happened their earlier uses because during those days, separation of this rare earth technology was not available. Over the years, science and technology developed, and with the development of technology, the separation and refinement of the rare earth was possible, and their usages were also become very, very multifaceted. A vast array of industries started using these rare earths. They grew in importance. Now, today these rare earth applications are used in high-tech activities and also to accelerate in our various other activities. Now, coming to overall application across the sectors, if you look at it, they are used in permanent magnets, glass industries, catalysts, metallurgies, medical activities such as MRI, X-rays, as well as some cancer treatment, in nuclear activities for nuclear control rods or shielding material, in defense, in the special warfare activities they are used, in certain other space research also used, and in phosphorus, where day-to-day activities were used in the smartphones and various other TV screens and many other such activities. These are used. So there we have become actually totally dependent on these rare earths in the nowadays and they are nowadays truly called as the vitamins of modern industry. Coming to rare earth minerals. 1 minute, please. My slide is slightly. I'm adjusting my slide. You can see me?
Yes, please. We can see the slide.
Yeah. Okay. Thank you.
RE minerals.
Yeah. Now coming to the rare earth minerals. Actually, rare earths are they occur as a trace elements or sometimes as minor elements, but very rarely as the major elements in the rock forming minerals. More than 250 rare earth bearing minerals have been identified till date. And since they are lithophile elements, or what we call they are rock loving elements, they are oxyphile elements, means oxygen, affinity for oxygen is very much there. So they generally occur as in the silicate phases, such as carbonates, phosphates, silicates, oxides, halides, borates, etc. And rarely or practically not in the sulfide or metallic forms. Among all these minerals, which are more than 250 or so many are there, most important minerals which are of economical importance are monazite, genotime, and bastnasite. And one more element is there, that is loparite. Majority of the global uranium deposits, they occur either in bastnasite or monazite. Genotime also occurrences are limited, but they are also very important. And only in Russian Federation, in Russia, it occurred in Kola Peninsula. That was a loparite mineral. That was a multiple or complex oxide of niobium, tantalum, uranium, and thorium, and as well as rare earth elements. They also occur as a borates, halides, and others where they are very, very insignificant. Among these minerals, now I'll talk about the very important mineral, that is a bastnasite. Bastnasite is the most important rare earth element in the world today. It is lanthanum cerium carbonate with fluorine, or it is called as a fluorocarbonate of lanthanum cerium. And it contains approximately 70% of rare earth oxides. It is most important source of light rare earths, occurs in carbonate and alkaline complexes as well as igneous other complexes. And major deposits which are found in this thing are, one is Mountain Pass in the United States, that is in California. Second is Bayan Obo deposit in China, that is the largest deposit in the world. And another deposit, that is Mount Weld in Australia. Second important mineral, that is monazite. This is rare earth phosphate that contains uranium and thorium. Chemically, it is called as cerium, lanthanum, neodymium, thorium phosphate. Approximate content of ReO is between 60 and 65%. It is a very important source of light rare earth elements. That is, as I said in the periodic table, mostly from lanthanum up to europium. Although other very limited, few other elements, that is heavy elements also occur in this. This occurs as accessory minerals in igneous and metamorphic rocks, and also concentrated in placer deposits. Majority of monazite deposits in the world, they are found as placer deposits. In India, we have got these deposits along the east and west coast, especially in the southern states. Third mineral is genotime. It is a yttrium phosphate. It has got the zircon structure. It contains about 60% of rare earth oxide, and majority of it is the primary source of heavy rare earth elements. Among all other minerals, this is one of the most important heavy rare earth element source. It occurs in granites, pegmatites, or granitoids, hydrothermal veins, metamorphic rocks, and often concentrated also in the placer deposits. As its properties are much similar to monazite, it also occurs along with monazite. In India, we get this in the Siri River in the central India. We recover it as a riverine placer deposit. Apart from these minerals, most important deposit that occurs on the clays, that is the clays or lateritic clays. It is nowadays it is called as ion adsorption clays. Earlier they were known as the lateritic clays. Now reclassification is made as ion adsorption clays. This is an important type of secondary rare earth deposit, very rich in heavy rare earth elements. This also occurs in China, in southern part of China, southern provinces. There are 3-4 provinces are there. In those provinces, these deposits of containing heavy rare earth elements in these clays occur. This is formed by weathering of the primary rare earth bearing minerals. This is the fertile granitic terrain is there, granitic metamorphic terrain is there. When it is weathered, that weathered soil, from that these minerals are released and they are transported in the regolith and they are concentrated as clays and preserved there. These REAs released during weathering are adsorbed onto clays. Clay minerals are very good for absorbing, whether it is rare earths or in other parlor we also call on the uranium. Uranium is also adsorbed on clays. So these deposits occur in southern China. These are very important minerals. Now coming to the geological occurrences of these deposits. These REEs occur in a range of igneous, sedimentary, and metamorphic rocks. They are normally divided into 2 categories. One is primary deposits and second is secondary deposits. Primary deposits are associated with igneous and hydrothermal processes. Secondary deposits are associated with sedimentary and weathering processes. Among primary deposits, we have got carbonate associated deposits, alkaline igneous deposits, peralkaline igneous rocks, iron oxide breccia hydrothermal type of deposits, and hydrothermal deposits. Under the secondary deposits, majority of the deposits occur as placer deposits. And within placer, we have got marine placers, we have got alluvial or riverine placers, and paleoplacers. Marine placers are basically along the, you can find along the beach sands, and they occur in India, Australia, South Africa, and China. Alluvial placers in Indian West Bengal area, we have got alluvial placers, very limited, about nearly 1 million tons of RUO we have found, but not very economical as of date, but alluvial placers are also there. And very important is paleoplacer. Paleoplacer is the placer deposits which were formed during the geological period. And these paleoplacers are found in Elliott Lake area in Ontario province in Canada, which is late Proterozoic, Archean early Proterozoic transition. These deposits were found in Archean early Proterozoic transition, where uranium quartz pebble conglomerates, pyritic quartz pebble conglomerates were deposited, and in that pyritic quartz pebble conglomerates, along with uranium, these rare earth minerals were also there in the form of monazite and branerite. Branerite is the uranium, calcium, uranium titanate containing rare earth elements. Apart from that, we have got lateritic deposits in Malawi and Australia, and iron adsorption clays, as I said, that is in China. These are the type of primary and secondary deposits. Now we'll go to the major deposits in the world. This deposit, Bayan Obo deposit in China, is the world's largest rare earth deposit. It is a polymetallic deposit and it contains rare earths as well as iron and niobium. This deposit was discovered in 1927 as the iron ore deposit. It contains nearly 470 million tons of iron ore. And in 1952 or so, this deposit was started, they started mining for rare earths. I think it was 1952. Just let me check it before I make the. Yeah, this deposit was discovered in 1927 and they started recovery of rare earths in 1957. Almost it took nearly how many years? 30 years for understanding the importance of rare earths to even the Chinese people. And subsequently, they accelerated their production from 1980 onwards. This deposit is occurring in metamorphosed dolomite and local swarm of carbonate dikes. And in dolomite, they have got banded iron deposits in the form of hematite, as well as these big lenses of rare earth bashnasite ore also occurs. The deposit is nearly 18 kilometers long and hundreds of meters thick, very huge deposit in the world. It is related to several episodes of carbonatite magmatism and multi-stage hydrothermal activities have taken place. Overall total resources of this are 470 million tons of iron ore, 44 million tons of rare earth oxide in the single deposit, world's largest and the major deposit, 1 million tons of niobium oxide, and RU grade of this ore is also very high, 4 to 6%. Ore minerals are essentially bashnasite and to some extent monazite. This occurs in the inner Mongolia, in the northern part. In the map, you see that is in the inner Mongolia area, the northern part of China. This deposit's location is there. Other deposits, iron adsorption clays, they occur in the southern provinces of China. There are large number of deposits are there. They are low-grade deposits, but since these deposits occur in deeply weathered, fertile granitic terrain, it is very, very easy to recover them, and it is very easily they are processed to production of rare earths. This is the world's largest heavy rare earth element deposits. Next is United States Mountain Pass in California, United States. This was one of the world's leading rare earth producer mine. This worked during 1960 and 1980. The mine closed in 2002. It is hosted by carbonatite alkaline intrusive complexes emplaced into older granitic terrain. REO content as of now is about 2 million tons. It is a MP Materials company is working on that. Recently, last year, they have published a data containing that 2 million tons of REO is available in that. And grade of the ore is 6%. Ore minerals here are bashnasite with less monazite and related secondary phosphates, that is secondary monazite or apatite related materials. The deposit is again very strongly LREE dominated, not much of the heavy rare earth elements. Next deposit is in Western Australia. It is called Mount Weld in the Goldfield region. This is again regolith related, but it is the regolith developed over the carbonatite complex, lateritic regolith. This was also called earlier lateritic deposit, but then subsequently they revised the concept. They call it lateritic regolith hosted deposit over carbonatite complex. Carbonatite intrusive complex intruded into Archean metavolcano sedimentary rocks. Ore minerals in this are secondary phosphate, that is secondary monazite, and apatite related minerals. Ore reserves as of now 32 million tons. These are ore reserves, not the actual REO content. REO content is only 6.45 million tons contained REO. And another interesting deposit is there. It is not economical as of date, but just put this deposit's name mainly because this is the world's largest deposit of uranium as well as copper. It is named as the Olympic Dam deposit. It is also called as IOC, Iron Ore Complex Group, or IOG. We call the Iron Ore Brexia Complex. This is a polymetallic deposit, and it is worked for essentially for copper, as well as gold is recovered, and uranium. So far, the REE, although they have estimated in the inferred category nearly 2,000 million tons, very low grade, 0.015%, that means only 150 ppm this thing is there. So far it is not recovered, but it is the potential deposit. In future, it may work out to be very economical. Other countries which contain the sizable uranium resources, I will just brush through these deposits. Brazil has got a good deposit in Minas Gerais. It is in the carbonate hosted deposit. Russia has got in Kola Peninsula, that is in the northern part, Loerezo area, where they are mining the uranium. Second thing is Vietnam. It is recently Vietnam has become a very big holding the resources of uranium. It occurs in the northern Vietnam, that in Lai Chu province. This occurs in the alkaline complex, that is cyanide complex. And of late, this Myanmar, in the Kachin state, which is close to China border, it has emerged as a key producer of heavy rare earth elements. But details about this mineralization is not well known. But it is understood that Myanmar is exporting its products to China for further processing. Greenland is another locality where it is since long, this deposit is quite well known, that is located in the Ili-Mozart Intrusive complex, alkaline igneous complex. It contains rare earths as well as uranium and thorium. It has not yet come up for production. And lastly, it is India, the placer deposits. I will discuss about the placer deposits of India in next slide. Next 2 slides I have. Where is that slide? India slide. Oh, now coming to the world resources. These resources are distributed unevenly in many of the countries. If you look at the distribution and all that, they're called, some people call it as them resources, whereas somewhere it is reported as reserves. There is a great confusion about the resources and reserves. Reserves are one where their confidence level for mining is very high. Resources include inferred, indicated, speculative, sometimes probable. So resource category or reserve category, which one is there? It is very difficult to make out from these figures. But for the generic purpose, we can understand that China is the largest resource country having the resources. Next is Vietnam. Australia is also having very good resources. India's tonnage is 6.9 million tons or 7 million tons of REO. Then South Africa is emerging. Number of countries are there in South Africa. Brazil, as I said. In the United States, that is the only deposit, that is the mountain pass in California. And Eastern Pass, it is shown here in the map that some monazite-related deposits were there in the eastern coast of United States. They occur in the North Carolina part, but they were associated with the monazite. Now that mining is not being carried out. And in Russian Federation, they have got nearly 10 million tons of rare earth oxides. Now coming to their global production, this is very interesting. This thing, I'll tell you about the global production trends. In this case, if you look at this graph, this is taken from the USGS. They have shown the production trends from 1956 till 2010 onwards, or 2010 onwards, up to 10. Actually, commercial mining of the rare earth minerals began during the 1880s. That is what I said in 1891. That was for the manufacture of gas mantles, and subsequently later on for the flint stones. And globally, they were mostly used for mantles, flint stones, and as a coloring agent. And that product, that produce, was supplied from India. India was the leading supplier of monazite or rare earths during the initial era. First, nearly 60-70 years, it was the India which dominated the rare earth market. The overall in this, there are 3 phases. Phases up to 1965, this is called monazite phase. From 65 till 1985, it is called Bashnasite or mountain pass phase. And 85 onwards, it is still Bashnasite is dominating, but it is called the Chinese era. Now we'll go by these three eras. How? In the initial stages when India was supplying globally, the United States during the 1940-41, almost 80% of import for the rare earth demand was made from India. And by 1944, practically 100% of United States requirement was made from India. And India was the global supplier of the rare earths in the form of monazite. When India got independence in 1947, the new government, they enacted Atomic Energy Act in 1948. And they took the decision because by that time, importance of uranium and thorium were known. So government of India, new government of India, the independent government, took the decision to stop the export of all the monazite, and that will be utilized for our indigenous industry, especially for the development of nuclear industry. So India stopped these exports by the act of, we call it as a Ilmenite Control Act, Ilmenite Control Rule in 1953 under the Atomic Energy Act. So after that, there were actually no supplies of rare earths to other countries. So this can be considered as the monazite pressure. This is the first crisis, which was rare earth crisis, is considered to be the first crisis. Next, what happened after the banning of India of the export? Other countries started exploring for the uranium. And in that, Brazil became more important. South Africa emerged as a major supplier. And also in 1949, while looking for the uranium exploration or uranium deposits, some survey for the uranium, accidentally in Nevada and California, when the surveys were being carried out by prospectors, they accidentally discovered some radioactive material and uranium. And they found this material, when it was checked by USGS, they found that to be the Vashnasite deposit. And later on, this deposit became the United States' biggest rare earth deposit. And they started mining this deposit. And from 1965 onwards, up to 1985, United States ruled the supply of rare earths in the world. And after that, what happened? When the China entered into the market in 1980, initial contribution of China was about 20% in 1980. And China's policy, open door policy, was declared in 1978, and China accelerated the production of rare earths, and which started with 20% share in 1980-85. By 2010 or by after 1990 onwards, practically 90 to 95% of the global share was contributed by China, and thus China became the monopoly in the world. This is the how, and even now, China is controlling more than 90% of rare earth related end-use products rather than the mining product. Mining is about 60 to 65% nowadays, but the end product or downstream industry products are more than 90%. Globally, majority of the countries are totally dependent on China. And this is how the supply chain in the rare earths looks. Rare earth supply chain is very complex. Actually, it spans from the exploration and mining of rare earth minerals, then mineral beneficiation or ore concentration. Then next is separation, refining, conversion to metals, alloys, magnet manufacturing, and end-use industry, integration with end-use. This overall is a supply chain. If you look in this supply chain, I got two lines. One is inner line I arrowed with the thick line, that is China, and upper one, it is the bluish color. It is a solid line up to certain this thing, and thereafter dotted line. Now I will explain this thing. Large number of countries are having the rare earth resources. Mining and exploration is very common. It is not very expensive or technologically very difficult. So majority of the countries which are having the resources, like in the monazite or basnasite, they are engaged in exploration and mining. This is not a very huge, what you call, technologically demanding situation. Next is concentration and beneficiation. The countries which are engaged in exploration and mining of deposits, they can also go for the concentration and beneficiation, because this is essentially physical activity in which physical beneficiation of these minerals is being carried out. After that, the biggest issue is the separation and refinement. This is called the choke point, where the technology is required, where the processing systems are required, chemical processing are required, and up to this place, majority of the countries are carrying out their exploration, mining, concentration, beneficiation, and mixed oxide of rare earths. That is TREO, they call total rare earth oxides or total rare earth chlorides. They can produce up to that. That's why it is dotted. But separation and refining is very, very important, this thing. And here many countries choke, in the sense this technology is not available or very expensive, as well as it is energy intensive. And here onwards, it is the only China which is controlling the system. Majority of the country, separation of the separate all the elements in the individual elements, in the individual oxide forms or individual metallic form, it is very difficult, and that is only the conversion to metals and alloys is being done in China. Other countries are having very, very limited scale, this thing, not on the large scale commercial activities. So next, all the three activities, if you look at it, conversion to metals and alloys, as well as magnet manufacturing, and then subsequently end use supplies. Up to magnet manufacturing is totally, it is controlled by China. And next, last is integration of these magnets and various other metals and alloys with the end use industries like electric vehicles, wind power, as well as aerospace, defense. They all depend on the magnet supplied from China. So this is very complicated. And if you look at it, it is the China which is controlling. That is how it is happening. First two stages are comfortably carried out by other countries. Nowadays, the United States, Australia, Japan, they are trying for the separation and refining the activity, but still their scale is not on a very large commercial scale. So still everybody is depending on China. Even Australia and United States, they are supplying the raw materials to China for processing, such as the MP materials and Russian one Lynx company or this thing, they are supplying it to China for the further processing. So this is a very important supply chain. Now coming to our Indian scenario, I'll tell you. We have got huge resources of rare earths, but in the form of monazite. All these deposits occur in the east coast and west coast of India. We have identified nearly 130 deposits. Majority of them are coastal stretches. Some of them are inland places in West Bengal. Out of these deposits, if you look at it, our monazite content is nearly 13 million tons. And from that, we can extract nearly 7 million tons of rare earth oxides. This is the India's position, but our mining activities are very, very limited. We have got only 3 mines as of now, located in the Kerala coast and east coast. In Kerala coast, it is called the Chauram deposit. Tamil Nadu, we have got Manola Kuruchi, and in the eastern coast, we have got Oscom deposit, that is Gopalpur and Chhatrapur deposits. These 3 deposits we are currently under mining, and mining in the sense processing for other minerals. Monazite comes as a byproduct, not as a major product. This is the part of the THM that we call total heavy minerals. Total heavy mineral content I will discuss it later how much it is there. Monazite is monazite content of these deposits varies from 0.4 to 4% of the THM. That is quite low. As a result, we cannot mine for monazite unless we mine for the other minerals. Monazite cannot be recovered. Next deposits we have got, that is in the carbonatite complexes. In India, we have identified 3-4 places where the carbonatite complexes of various sizes have been identified. Biggest one important was in Ambadongar carbonatite complex, that is in Udaipur district in Gujarat. It is a part of the Deccan Volcanic Province. In the northern part in Rajasthan, we have got number of carbonatite complexes in Barmer districts and Nevania area. In northeastern India, we have got in Assam and Meghalaya. They are in the form of Sung Valley, Jasra, and Samchampi carbonatite complexes. And Tamil Nadu, we have got Sevatur and some Samarpatti carbonatite complex. In this, exploration work is going on for the rare earths. As of now, 1.29 million tons of rare earth oxide in these deposits, especially in Ambadongar and Barmer area, have been identified. But these carbonatites are in a very different sizes. Some of them are in the veins, plugs, or this thing. Only one deposit that is a bigger size, that is of Ambadongar, of nearly 30 kilometer wide. Our current status in India with regard to the rare earth resources, it is majority of our deposits, they occur in monazite, very large resources, as I said, 130 deposits. They occur in 4 major states, that is Andhra Pradesh, Orissa, Tamil Nadu, and Kerala state. Monazite concentration, as I said, it ranges from 0.4 to 4% of THM, total heavy minerals. Whereas we are carrying out mining at 3 places, Chawra, Banola, Kurichi, and Gopalpur. And product of monazite is a byproduct of the other heavy minerals. With regard to current activities, mining and mineral beneficiation is being carried out, that is monazite concentration. And on this, we have got, this is the limited activity, rare earth separation and refining facilities. We produce mixed rare earth oxides and rare earth chlorides. There are 2 projects for production of permanent magnets. Initially now they have been taken up, and rare earth metals. Both are on the laboratory and demonstration scale production. They have commenced. One is at Bhopal and another is in BRC's Vizag plant. But for the value-added products, India still depends on the imports from China. Majority of our imports are from China. This is the biggest challenges for our India is concerned. As I said, we have got huge resources in the form of monazite. But our contribution is less than 2% to the world production. Because our deposits are also low-grade deposits. To produce more rare earth than monazite, huge quantity of material has to be handled. This is the biggest constraint we are having. Technologically also, our production is limited. We go only for the mixed oxide, rare earth mixed oxides or rare earth mixed chlorides. And there are huge processing gaps. Our technology is not that advanced to separate the individual rare earth oxides. This is one major drawback. Third is dependence on imports for the high-end applications. We import majority of our high-end products only from the China. And major bottleneck for us is the regulatory and policy bottleneck. Because Indian rare earths, they occur in the form of monazite. And monazite contains, on an average, about 60% rare earth oxide, 8 to 10% thorium oxide, and 0.3% uranium oxide. Both uranium and thorium are radioactive. And Because of these things, and as per the Atomic Energy Act 1948 and subsequently it is 1962, these minerals are controlled under the Atomic Energy Act, and only government agency can process this monazite. As a result, only agency which is handling this monazite is Indian Rare Earths Limited. And no other company, whether it is private or any other, this thing can handle the monazite. There are private companies engaged in processing of ilmenite or other things, but not the monazite. Monazite has to be handled only by the IREL. This is the regulatory constraint and policy bottleneck. Because of that, only one agency is engaged, and the production of R&D activities are limited to only one company. Unless big investments are made in this, lot of technological development has to be, advancement has to be made, then only it is possible to separate these rare earth elements on the individual basis in the form of individual rare earth oxides or subsequent high-end products. Second thing is there is environmental constraints, because our monazite, when we process the monazite, it creates radioactive waste. And a lot of monazite or large quantities of monazite are occurring along the coastal tracts where a lot of settlements are there, social activities are there. So socio-economic problems will be there. We cannot produce the monazite and process this thing at every place. Unless clearances, there are CRZ regulations are there, many constraints are there with regard to that. These are the big constraints are there. And lastly, the investment and R&D challenges. This is huge investments are required, as well as R&D activities are to be taken up on priority, then only these things. And besides that, it is not only the monazite. We need to look for the rare earth minerals which are devoid of radioactive materials such as uranium and thorium. That is the Bashnasite. Bashnasite deposit, as in the China, that is the free from radioactivity. That is why it is easier. There are not many environmental concerns. It is easier to process compared to monazite. When you process monazite and process Bashnasite for rare earth production, you will find it cost-wise, it is 1:4. Monazite processing will be very expensive, nearly 3 to 4 times compared to Bashnasite. These are the constraints one has to overcome. And this is what I like this thing. Thank you very much.
Thank you, Arvind sir. It was a pleasant and very informative lecture. I think all these should be there in the syllabi of students at MSc, because unless and until we know what are our drawbacks, we will not be able to improve upon our strategies at national level. So thank you very much for a valuable information. Now I would request Head Department of Geology, Mr. Dr. Devdtta Upasani, to give word of thanks. Devdtta, please.
Yes, sir. Thank you so much, Kulkarni sir. Yes, so I would like to begin by saying that it was an amazing beginning to this year's Earth Science Week celebrations, especially remembering our former head of the department, Professor P.V. Soni. And though I have not directly learned from him, but we still follow many of the examples set by him in teaching at Ferguson College. So first, I would like to take this opportunity to thank Professor Jere Lips, who probably very early in the morning woke up to give us his lecture, his very short lecture on geology, past, present, and future. So he really touched upon point wise on the past, that is about introduction to how plate tectonics developed and the time scale, and then in the present he talked mostly about climate change and the nature of climate change that is happening. And from a future perspective, he touched upon two topics, that is astrobiology and astropaleontology, and the problems that we might face because of the rising population. So thank you, Professor Lips. Secondly, let me take this opportunity to thank Mr. Arvind Avati also, because many of us talk about REs but aren't very much aware of many of the things that you talked about today. So it was a very informative presentation where you talked about the properties of REs, the applications of REs in different fields, and for geologists mainly about the minerals and rocks which would bear REs. It was very interesting to look at the world occurrences and next to the occurrences in India that are known as of now. Um and most important, it was very nice to understand about the challenges that we would face in the RE exploration. So I'm sure your talk must have inspired many of us to work more towards RE, and probably we can start by searching for Basna site to start with, along with the other things in our research. So yes, once more, thank you so much, Avati sir, for your presentation. Finally, before we end today's session, there are two things that I would like to inform. First is about tomorrow's program. So tomorrow we'll be beginning exactly like today at 6 p.m. And we have Professor Stanley Brun from the USA who will be delivering a talk on issuing and reading of stamps for insiders, outsiders, and profits. So I think it's going to be another interesting talk tomorrow. So stay tuned for that. And secondly, because of limit of number of participants on Zoom, many of the ones who are there in the meeting, many of our friends or um, colleagues would have not been able to join. So you can just inform all the others who couldn't join that they can watch the same live on YouTube tomorrow in case this Zoom limit fills up. So you can at the same time you can watch it on YouTube live also. So that's all from today. I would like to finally thank all the participants for taking out time on a Sunday evening in India and listening to both the talks. And see you tomorrow. Thank you.
Kulkarni sir.
Thank you very much, everybody. We are
Yeah.
closing for today, and tomorrow we hope same number of participants they do come. Thank you. very much.
कुलकर्णी सर
हा,
चॅट
बोल.
मध्ये काहीतरी 2-3 काय आहे ते पाहता का?
काय काय
चॅट मध्ये
ओके
कोणाच्या काही कमेंट्स आहेत, काही प्रश्न आहेत का पाहता का?
नाही कमेंट्स बहुतेक त्यांनी हे केलेलं आहे कारण का चॅटमध्ये नो ऑडिओ बद्दलच होतं जास्त.
अच्छा.
डॉक्टर ॲडव्होकेट संध्या देशपांडे दे हॅव communicated just thanks, and those who are not able to hear, audibility wasn't there, so that is a major problem that we have. But this is for information that the same talk can be seen on other Zoom,
मिशन देवराई YouTube
Mission
चॅनल.
Devra YouTube, yeah, and all older sessions have also been posted there, so you can please have look at all these Mission Devrai's personal meeting Devrai shows, and everything is available on those, even past sessions.
Yes.
Yeah.
So we are closing today's session.
Yes, because nothing much, no questions are there in the chats.
Yeah.
So I hope everyone, and both the talks were really valuable and informative. So